Good morning. So we're moving on here, getting into chapter 5 in your textbook. And up to this point we've been looking at forces and motion in one dimension. At this point we're ready to start talking about how to add force vectors in multiple dimensions and when they're at angles to each other. So as a quick review for vector addition, up to this point we've been able to do this sort of thing pretty easily. If I have two force vectors that are pointing in the same direction, basically we add them. So a 50 Newton force to the right plus a 30 Newton force to the right is going to be 80 Newtons. And you'll see this R letter here. What that stands for is the resultant force. And so you'll see that notation from time to time. The second example I have here is pretty similar. They're both on the same plane. The 50 Newton and the 30 Newton force now are pointing in opposite directions. So in this case we're going to subtract the 30 Newtons from the 50 Newtons, and my resultant force is still a 20 Newton force to the right. But what do you do, and this is the focus of today's lesson, when you have a 20 Newton force being added to a 10 Newton force and they don't point in the same dimension? Basically what you have to do is resolve the 20 Newton force, which is at a 45-degree angle, into vector components, which will then allow you to add the vectors and then bringing them back together into a resultant. So I'll walk you through this process. First thing to realize here is the 10 Newton force is all horizontal. So in that case, no part of that force is at an angle and we don't have to resolve it into components. So we're going to focus on the 20 Newton force, and then we'll break it into X and Y components, and then we'll be able to add it to that 10 Newton force and figure out, at the end of the day, we want to know what's the net force acting here on this object. So a bit of a trig review for those of you guys who have taken it, and those who have not. It's pretty straightforward, so just kind of follow along here. So we treat this original force vector as the hypotenuse of a right triangle with an angle of 45 degrees. So if I were to kind of rebuild this triangle, it would look like that, and my right angle would be there. And there are some trig identities that you'll want to either memorize or write down. So your sine of angle theta is equal to the opposite leg of the triangle divided by the hypotenuse. Your cosine of angle theta is equal to the adjacent side of the triangle multiplied by the hypotenuse. And then the tangent of angle theta is equal to the opposite leg divided by the adjacent. So how does that work? If I look at this triangle which I have drawn here, my 45-degree angle is going to be representative of angle theta. I would take my calculator and I would plug in sine times 45 in parentheses, and then I would multiply that value times the hypotenuse, which is a known value in this triangle of 20 newtons. And that would allow me to solve for the opposite leg of the angle. So the opposite and adjacent sides are referenced to the angle theta. So here's my angle theta, the 45 degrees. This is going to be my opposite leg of that triangle, and this will be my adjacent leg of the triangle. And notice how both of those are always going to be next to the 90-degree angle, not the hypotenuse, which is 20 newtons. So what do we do? So we want to find what we call the x component and the y component of this force vector. So it turns out any force at an angle can be resolved into components, and then we can add those components, and they're a little bit easier to deal with. But one thing I want to make sure you understand right now is once I resolve a vector into x and y components, I throw away the original vector and then I'm working just with the components. So, in order to add the 20 Newton force to the 10 Newton force, I need to resolve this 20 Newton force into its x component here and its y component here. Then it'll look a lot like the previous example. I should be able to add, two forces pointing in the same direction in the x dimension. And then we'll deal with that y component at the end. So let's resolve the legs of this triangle first. So my x leg here is going to be sine of 45. Hold on. Okay, so I had to switch those. The y leg is going to be the side opposite the angle here, and that's why we're going to use the sine. So the sine of my 45-degree angle times the hypotenuse of 20 newtons. So basically I'm using this equation right up here and I'm simplifying it. So I take the sine of 45 and multiply by the hypotenuse, and that's going to tell me that the y leg, vertical component, is going to be 14.1. Now obviously, if this is a 45, 45, 90 right triangle, the x and y components are going to be the same thing. So when you do the cosine of 45 times 20, you should get the same answer. So if the angle is not 45, let's say it was a 30, 60, 90 right triangle, well then those legs would adjust accordingly. So once I know that this y component is 14.1 and this x component is 14.1, the way to deal with it is to make a list over here like I've done of my x components and y components. So what I have here is an x component of 14.1 in the positive x dimension. That's important. If it were pointing left, it would be a negative 14.1. I'm going to add that to my original other force vector of 10 newtons, which was all pointing along the x-axis, and those add up to 24.1. So we call this the sum of the x components. The y component list is short. There's only one thing here, and that's because there's only one portion of these force vectors that is pointing in the y dimension. My y component, like we talked about, was a positive 14.1, and that's because it's pointing up. So ultimately my resultant vector here has a sum of the x components of 24.1 and a sum of the y components of 14.1. And what we need to do is rebuild those into a right triangle to create our resultant vector. So that looks like this. So here's my sum of the x's, here's my sum of the y's. I'm going to draw these two vectors tip to tail. And what that means is the tip of one of the vectors will meet the tail of the second vector. And my resultant, this is super important, is just like our displacement vectors from that lab we did a while back. Where did we start the day? Where did we finish the day? So that's going to be the hypotenuse of this right triangle, which we can solve for by using Pythagorean's theorem. Pythagorean's theorem is a squared plus b squared equals c squared. So my a squared value is 24.1. I'm going to square that to get 580, plus 14.1 squared gives me 198, and that's going to equal the hypotenuse squared. So add those, square root 779, and my c value, my hypotenuse, or my resultant, is going to be 27.9 newtons. So that's the answer at the end of the day. When I add these two vectors, okay, a 20 Newton vector at an angle of 45 degrees plus a 10 Newton vector pointing straight to the right, those turn into basically one vector pointing northeast with a magnitude of 27.9. So what is the angle here? We should probably take care of that, because a lot of times we're going to want to know, well, what is the direction of that final vector? So to find the magnitude of that angle, we're going to redraw everything we know about this triangle. So we knew this leg was 24.1, this leg was 14.1, and now we're going to use a inverse tangent function. So we're going to say tangent to the negative first of the angle of interest, theta, is going to equal the opposite divided by the adjacent legs of the triangle. So some of you might call that arctangent. And so what you do here is you'll take your opposite and adjacent legs. So my opposite leg is 14.1, and I'll divide that by my adjacent 24.1. That gives me 0.58. So I'll take the, on your calculator you have to find the inverse tangent function. So for me I have to do a little shift, tangent of 0.58, and that gives me my angle of 30 degrees. So that would be my final answer. I've got a force, 27.9 newtons at an angle of 30 degrees, and we would say north of east. So we're referencing the horizontal x-axis here. We'll also use a 360 degree directional system, but for now we're going to express our vector angles as north of east, or north of west, or referencing one of the primary xy axes. Alright, in 3 minutes here, let's take a look at number 9. So on your problems this week, number 9 was a swing example, and so you might want to open up your book to that one. We're in chapter 5, number 9, and you have a swing hanging there. It tells you there's 2 tension forces of the ropes. Each of those is 2.28 newtons, and it tells you that the angle that those ropes make with respect to the vertical is 13 degrees. And you're being asked what the total force is in the vertical dimension. I think your book says what is the combined force of the 2 ropes on the swing. So the combined force, first thing we have to realize is that there are some horizontal forces here. Those are going to cancel each other out, so we don't have to worry about them. So really what we need to do is figure out the 2 vertical components of these tension forces and then add them together. So I'm going to start by drawing my right triangle here. Here's my original force vector, 2.28 newtons. Here's my angle, 13 degrees. So in this case I'm going to want to do the cosine of 13 times 2.28 to solve for the magnitude of the tension force in the y dimension, which happens to be 2.22, so it's not much different, and that's because it's not a very big angle. I'll add both of those. 2.22 times 2 gives me 4.44, which is your answer to the problem. But let's take it a step further and find the mass of the swing. We realize that in the free body diagram I've got 2 forces of 2.22 newtons up that are balancing the weight of the swing, which must be 4.44 down. And we can set 4.44 equal to the weight, mg, and then solve for the mass of the swing by dividing 4.44 by 9.8. So I think you probably are going to have to do that in problem 10, which is a little bit more challenging. So good luck with that one, and let me know if you need help. Alright, good luck this week.